In our previous video, we discussed what a random variable is. We also discussed discrete random variables and continuous random variables. In this video, we will discuss what probability mass functions and probability density functions are. Let's look at an example first to understand what probability mass functions are. Let's say we toss a fair coin 5 times. We are interested in knowing the number of times heads appear, and we are not interested in the head-tail sequences that occur in the results. So, we can take a discrete random variable x that denotes the number of times heads appear in the results. Now, if we toss a coin 5 times, heads can appear 0 to 5 times. So, x can take any integer value from 0 to 5. If we toss a coin n times, x heads can appear in the results in NCX ways. And in a particular sequence of n trials, if p is the probability of getting a head and 1 minus p is the probability of getting a tail, then the probability that the particular sequence will contain x heads and n minus x tails is p to the power x into 1 minus p to the power n minus x. Please note that the trials here are independent of each other. Here we toss a fair coin, so both p and 1 minus p are half. Therefore, if we toss a fair coin 5 times, the total number of outcomes is 2 to the power 5 is equal to 32. P0 is equal to the probability that no heads appear in the results is equal to probability x is equal to 0 is equal to 5c0 into 1 by 2 to the power 0 into 1 by 2 to the power 5 minus 0. Similarly, the probability that one head appears in the result is probability x is equal to 1 is equal to 5c1 into 1 by 2 to the power 1 into 1 by 2 to the power 5 minus 1. In this way, we can say that if we toss a fair coin n times, the probability that x heads appear in the results is NCX into 1 by 2 to the power x into 1 by 2 to the power n minus x. That is equal to NCX into p to the power x into 1 minus p to the power n minus x. Here, p is the probability that a head appears when we toss a fair coin once, and 1 minus p is the probability that a tail appears when we toss a fair coin once. So, we can say that if px is the probability of getting x number of heads while we toss a coin n times, then px can be written as ncx into p to the power x into 1 minus p to the power n minus x. This px is called the probability mass function of the discrete random variable capital X. Please note that if we toss a fair coin 5 times, the summation of probabilities that x will take any values between 0 to 5 is summation x is equal to 0 to 5 px. Here p is equal to 1 minus p is equal to half. So, if we do the calculation, then summation x is equal to 0 to 5cx into 1 by 2 to the power x into 1 minus 1 by 2 to the power 5 minus x will be equal to 1. Here, x is a discrete random variable. We perform n number of independent trials. P is the probability of success and 1 minus p is the probability of failure. If px is the probability of x success and n minus x failures, then px is equal to ncx into p to the power x into 1 minus p to the power n minus x. Such discrete random variable x is called binomial random variable, and px is the probability mass function of capital X. In the above example, x is a discrete random variable. If x is a continuous random variable, then we can take a function f such that f is defined for all real numbers x belongs to minus infinity to plus infinity, and it has the property probability x belongs to b is equal to integration fx dx. In other words, the probability that the continuous random variable x can take any set b of real values can be denoted by probability x belongs to b is equal to integration over b fx dx. The function f is called the probability density function of the continuous random variable capital X. So, the probability that x can take any real values between a and b can be denoted by probability a less than equal to x less than equal to b is equal to integral fx dx over the limits a to b. Now, let's look at an example. Let's say x is a continuous random variable that denotes the amount of time a computer functions before it breaks down, and the probability density function of x is given by fx is equal to 1 by 100 e to the power minus x by 100 when x greater than equal to 0, and it is equal to 0 when x is less than 0. So, the probability that the computer will break down after 100 hours of use or the computer will function up to 100 hours is probability x less than 100 equals to integral fx dx over the limits 0 to 100, and after calculation it is 0.632. In other words, there is 63.2% probability that the computer will break down after 100 hours of use. I hope this helps. Interested viewers who want to know more, please refer to the playlist Statistics for Machine Learning or visit the website of the Security Buddy. You may also want to subscribe to us and get notifications on recent videos.